Hello boys and girls. So I will make a video on the functional form of the Shannon entropy, so the logarithm, and arguing why it is there or what would be alternatives. I want to talk about the Thales entropy, arguments against it. Here's an 80s paper that has some axiomatic approach. I will talk about this. But as I was writing the script, I was more and more feeling that I should, especially for the people without a physics background, explain the different earlier notion of entropy that is, however, related. You see a little bit of a timeline here on screen. You had, like, in the earlier 19th century, the emergence of the phenomenological theory of thermodynamics. I will sketch this out in the next video, and in this video motivate why the theory shall look like it does, based on an example in this video, also together with a computer simulation that you can run yourself, that motivates this in some sort of combinatorial way. We have sort of the statistical mechanics approach to justify the phenomenological theory of thermodynamics. These are two physical theories that are extremely strongly interlinked. And I want to do this because I want to talk about extensivity and addition, for lack of better words, which together with probability theory justify the logarithm, and which goes into deviations from this. But in the physics theory, which come earlier, there's the justification is a little bit different than in this 1980s axiomatic approach, and I want to work this out a little bit. So in this video, you will understand in one simple toy model, but not trivial toy model, certain like entropic pressures, effects, equilibration of temperatures. You will get an intuition for temperature and entropy and why it does what it does in physics. Also, I made a bunch of very nice, I would say, ChatGPT images, which I really love. And you will in a second understand what they are saying. So let's get into it. The main thrust of the video is a simple game which you can actually also literally play at home. I mean, game is maybe too much said, but it's a sort of like a statistical setup that you can play through, and for which I also, you see here these computer simulations, which I will explain. And they are related to this statistical or probability theoretical toy example, which are, however, an analog of physical situations. And I will start the video here with explaining you this setup. Okay, so let me first motivate how it mirrors the physical situation. So the physical situation is that we want to talk about heat. We want to talk about particles in a box, let's say, and heat transfer in and out of these boxes depending on the temperatures. I use the word temperatures, energies, and these kind of quantities already in my common description, but we will at the latest in the next video see what temperature really means. We will also define it here in this video, but you have a lot of intuition which I can play with, by which I can explain to you first the physics scenario. So you have this dog here. He's sweating. The dog doesn't play a role at all. This is just that you see the dog is outside and it's hot outside because, of course, there's a desert, and outside you have air. There are some particles which make the dog sweat. They carry some energy, right? And then you have the room. Let's say until previously the AC was on. It's like a nice climate inside of the room. And of course, that if you turn all the AC off and wait at least a few days, then it will also get hot in the room. That you notice from your own experience. So if there is some sort of interaction, right, maybe through the walls, through the glass, it does not even need that particles, like air particles, actually move through in some sense. Just from all the physical materials interacting, the room will eventually warm up, so the coldness will be gone. since, in physics theory terms, the outside is a sort of bath. There's like a big reservoir, all technical terms, with a lot of the energy as a whole. It is the cold room which will actually like rise closer to the outside. So this is the situation that we want to understand. We want to understand why does it actually happen that the temperature goes up? Why does the temperature encroach on the outside temperature? We will see this in this video. And the situation that we use as an analog to this, fairly close analog as far as simple simulations go, is this card situation that you have here. You have two carpets, left one, right one. I will use left, right interchangeably with green and purple because this is the colors of the carpet. Each of them has a fixed number, I will later call it capital N, of cards. So for example, the green left carpet has 10 cards. The right purple carpet has 16 in this case. And a certain number of cards are in an up state. They are flipped up with, you see the face of the card. And the others are down. So in this case, there's 7 up and there's 3 down. 7 out of 10 are up. What is on the cards does not matter at all. Here I choose some energy quantities just for the theme, and likewise here I chose some weather related images. But it is purely about the state in which a card is in. And now comes the game rule. What we do is we use some random number generator, a uniform random number generator for each side. So let's say you have a 10-sided die, right? Or maybe use a computer program to sample a number between 1 up to 10. So you roll your 10-sided die, you get a number, it indicates one of these cards. Then you have a card picked on the left-hand side. You do the same thing on the right-hand side. You roll a 16-sided die, you get one card. Now, if the cards are both in an up state or both in a down state, then you just ignore the roll. Right? Nothing happens. If, however, this is not the case, if one of these two cards that you randomly chose is up and the other is down, right? It doesn't matter if left or right. What you do then is you change the state. So, for example, if I roll, I get this card and this card. Then, since this is down and this is up, I flip over this card, this gets down, this goes up. And likewise, if I chose this and this, then nothing happens, and I roll again. And I do this, and in this way, the state is transferred, right? So the number of up cards overall here is 7 plus 4, so 11 out of 26 cards total. 11 out of 26 card total is flipped up, and this process that I just described does not change either of these numbers, right? So there's just like an energy transfer, if you want, to the extent that this is just the physics language. We say the up state is like the let's say high energy state, versus the down state is the zero energy state. The simulation rules that we described allow for energy transfer between the two sides, and if an energy transfer happens, depends on which card we've sampled. Okay, so these are the rules. You can, as you imagine, you can play them yourself. And the thing is that what happens depends a lot on the ratios, right? So I call the total number of cards 10 here, capital N, and the number of flipped up cards lowercase n on the left side. This ratio, like here 7 out of 10 in this case, this will play a crucial role. And if we now follow these rules that are laid out, we get, and this is just an observation, but we will do a mathematical derivation of this basically. We get a convergence actually of these ratios. So if you play this long enough, then spoiler, while the number of 11 up cards stays the same overall, the ratios will equilibrate. And this is sort of the phenomenon that you at the end of the video will buy into, and maybe you can already intuit this. Okay, so having here some information, so I will focus on the top row images. So here is the same game, the simulation, just that we get a little less jagged curves. I bumped up the numbers. So here we have the same scenario here, but I multiplied all numbers with 5, right? So I have on the green carpet 50 cards, and 35 of those are flipped upside green cards. So I have just multiplied all the numbers with 5. And same on the other side. On the other side, I have 16 times 5 cards, and 20 of them are at the start flipped up. And here we see, if you play this game, then no, it's random. It goes sometimes up and down, but it tends to, the green line tends to fall. And this is, I mean, you can intuit it. This is because it's because a higher fraction here is up and a lower fraction here is down. Then at the start, it's a lot more likely that the first acceptance of exchange will be one where you choose an up here and a down here, right? Just because there are more up here and down, more down here, it's more likely that you choose a combination like, you know, this U card and this card, or some equivalent, you know, up and down here, then that you choose one of those and one of those 4, right? It's just there's less likelihood that a combination between down here and up here happens at the start. And because, and this is basically, you know, this is already giving away the game, because there is just a probabilistic setup that exchange happens more often if more up cards are on this side, relatively speaking. There's a sort of a pressure of losing energy. The blue carpet, the green carpet will lose energy at the start, and then eventually these, and you can see this in this picture. Eventually there comes like an equilibration of ratios, right? So where there's some number, like 40% on this side, 40% on this side, roughly checks out with the number of energies, like 11 energies on 26 cards. And then we are there, and you know, if I let the game go on, then it can move in either direction again. It can move away from it. But whenever one side has like an overpowered energy ratio, then this overpowered energy side is also more likely to give it off again, right? And so there's like this is what I meant with entropic pressure. We will talk about why this word. There's like a pressure against the state. So there's like a force just with these probabilities, and you do not have to have studied physics. You can intuit this maybe, that if you have more up cards, then it's more likely to find a situation where you have to give it off. And so there is some balancing point. There's some certain fraction around which the game, like the scenario, will then fluctuate. And this is the equilibrium temperature, or the equilibrium temperature will be a function of this ratio in this case. Okay, here's the same situation where I do not use multiplication by 5, but multiplication by 100. So on the left-hand side, I have 1,000 cards and 700 are flipped up. So the graph is a little bit smoother. I also do not go on with simulations forever, but I stop at 3,000, and you see there's the same phenomenon. The fraction, they go in this case to the same fraction that is determined by the ratios of the numbers here. Okay, and later on I will go back to this picture. Oh, I hope this was, yeah. I will go back to the picture and also explain the bottom images. But I will also already tell you the black line here is related to the total entropy of the system, right? We will discuss everything in terms of probabilistic pressures, but in the thermodynamic theory, the same thing is described in terms of this entropy curve. And then we can also define a system for any such situation. Okay, so I just want to get the basics across. This first paragraph is now just to remind you that the multiplication plays a big role in the Kolmogorov axiom. So here's another situation. We talk about dice. If you have a 6-sided dice and you roll it, then each side, each one of the 6 sides has a chance of 1/6 to come up. If you have 2 dice, you roll them one after the other, and you look at the first one, the second one, you respect the order. Then if the dice are independent, you know that there is 6 times 6 many possible outcomes, right? So 1 1 1 2 1 3 and so on and so forth, eventually 6 1 6 2 6 3. So there's like 36, and it's also clear that respecting the order, there is all these 63 states are equally likely, so the chance of rolling either of these ordered combinations is 1/36. So there's this relation between the number of microstates, number of different outcomes, and the probability. It's like you divide it basically in these uniform distributions, uniform priors at least, and to get the number of combined states, you have this multiplication. I emphasize this because this will play an important role when we talk about entropy, especially when we talk about the logarithm, extensivity, and arguments for while in the Kolmogorov theory, multiplication plays a role. We seek for arguments why addition plays a role, and so this is like a spoiler for the logarithm topic of the next videos. Okay, so quickly formalize the game. I basically already introduced this. We have these 2 sides. We have the capital N cards on each side. We have the small n number of flipped up states. We have the conserved quantity of the number of flipped up states, right? 11 in our case. The exchange does not alter this number. And then I have introduced this auxiliary language. We don't have to use this, but if you have a unit of energy like a constant var epsilon, which represents some quantum of energy, then instead of talking about the small n, the number of flipped up cards, I can also talk about the energy of one side, right? At the start, the green carpet has an energy of 7 units or whatever. Okay, and we will not need this technically to derive the effect that we see, but we need the total number of states to talk about entropy later. And by states, I mean here, like if you look at one side, right? Let's say of the left side where we had 10 cards, and I fix the energy, which is really the only thing we care about to do the simulation. We have 7 out of 10 is up, energy of 7 with 10 possible cards. Whether this card is up and this is down, or this is up and this is down, of course, does not affect the chance of a transfer coming about, right? So we do not really care. We only care about the ratio. The probability that the energy transfer happens in either direction is only determined by whatever the ratio is. We do not care which individual cards they are, right? So for fixed energy, there is a bunch of different states, right? So we can exchange these the place, the location of these 2 cards. It is the same effective scenario. So the energy is what we care about, but there are like micro states that are underlying, and this is what I mean by like we count the number of states per fixed energy. And if you do a little think, then you realize that this is just given by capital N over small n with the binomial expression. So we say take 7 out of 10, and how many possibilities are there to take 7 out of 10? This is exactly the number of combinations. And so this is the number of states with fixed energy is this n over n expression here. The number of total states, when we say, oh, there's so much energy on this side, so much energy on this side, how many possible states are there in total with rearranging the one on the left and the right? By my dice argument, this is just a multiplication of this. So 2 binomial expressions, these coefficients multiplied together is the total number. And the energy is, of course, just 11 times the energy unit. Right? Again, we don't need this energy. This is just so you understand the physics later on. Okay, and so here we have, so that you get a feeling for how this binomial coefficient looks like. If I will try to be short because you most likely already know this fairly well. I have here the simplified situations where I do not take 10 cards because the numbers are too big just to talk about it, but just 2 cards, right? Let's say I have the situation, 2 cards on 1 carpet. The carpet color does not matter here. It's clear that there is, like with this, the card order fixed, there's like 4 different possible states that this thing can be in overall. 0 energy, 2 energy, and then there's 2 ways of having 1 energy, right? So in particular, if I have 2 cards and I say I'm interested in the states which have 1 energy, then there is actually more different options than in this more extremal situations, right? And this again, this is 2 to the power of 2 4 combinations, and this breaks up into numbers which are given by Pascal's triangle, right? So we are here in this row, 0 energy, one way to get there, 2 energy, 1 way to get there, 1 energy, 2 ways to get there. Here you see also, like, you know, if U denotes up and D denotes down, then you can calculate the each row in Pascal's triangle like this. And what's interesting is here, why I even make this picture and this graphic, is that if we have here, this corresponds, I think, to 6 cards, the situation where you have 6 cards on a carpet. If you only, like, if the 6 card on a carpet situation only has 1 energy, meaning only 1 card is flipped up and 5 are flipped down, then there's of course 6 different ways in which the cards can have this energy, like 6 different micro states that correspond to 1 energy. This is exactly this quantity. If there's 0 energy, then this is 1. And the interesting thing is that the microstate which have the energy for which there are most microstates is somewhere there in the middle, right? So if I have like 100 cards, then the situation with an energy of 50 has a lot, while the energy 2 has a lot less. So this distribution is this symmetric sort of distribution with a maximum in the middle. And this already corresponds in a way to information, right? In physics, in thermodynamics, but even in quantum mechanics, you have observables. The macroscopic quantities are deemed observable, the volume and maybe the energy. And holding the energy fixed, like having measured the energy, you have the least information about actually the underlying micro situation when like at a particular certain spot, right? So there's a relation between all possible like slots, all the possible cards, and there's a certain like energy value somewhere in the middle where you have the least information about which particular microstate there is. And this is already like it's just an elaboration that goes towards this entropy concept, because we will also see this process of equilibration of temperatures. We will talk about it in terms of probabilities in this example, but I motivate all this capital omega talk to show you that in this particular combinatorial example, it will also correspond with like a maximalization of number of microstates. Spoiler. Okay. Yes. And now the part where I formalize the heat transfer again. This is also fairly simple. I've already discussed what happens. Formally, like a particular energy situation, like regarding how much energy is currently on the left side, how much energy is currently on the right side. If an energy transfer happens from left to right, for example, then it just means that, you know, 1 card is flipped down and on the left side, and one card is flipped up on the right side. So these numbers, these energy numbers, are just transferred. You have minus on one side, plus one on the other side. The sum stays the same. This is just a formalization of this process. And now this argument for when does actually like a energy transfer happen. So firstly, we look at these combinations. The combination where if we uniformly pick one card from either side, as we have to in our game, the chance that we pick a flipped up card on the left side and a flipped down card on the right side, so that an energy transfer from left to right happens, is naturally proportional to the number of up cards down times the number of down cards on the right hand side, right? So it's clear that if we just look at left up, right down, the chance that we get into the situation is higher if we have more up on the left side and more down on the right side, right? So this goes linearly in each of these components. So I hope this is intuitive, that this is the correct proportionality. And in the same way with multiplications, you can argue for the other ones, right? So this is just this is the chance of hitting the right to left motion, and then there are certain combinations that where nothing happens and you go to the next sample iteration. So if you both sample up energy, nothing happens, and if you both sample down energy, also nothing happens. These numbers, you can sum them up. They sum to the totality. And so given that we have an acceptance, so assuming, like, conditioning on we are now going left or going right, the chance of going left to right is exactly proportional to this and divided by this denominator, right? Okay. And so what is interesting is we saw that sometimes energy goes left, sometimes energy goes right. The odds of that happen is literally the odds of the probabilities that we just defined. And if you do this, since the denominator is the same for all, and this is just a normalization of the probabilities, since the denominator is the same, they cancel out if you compute the odds, and then you get the product of small l times capital L, r times minus lower r, and so on. And the other direction is exactly with the letters, with the indices swapped. And then you can divide through it. You can do this in your head. You get this sort of expression. So this is the odds that an energy transfer from left or right happens. Leaving aside the situations where nothing happens, you just go on to sample. That's what this conditioned on accept means. This is just to take account that also nothing can happen. But this is not interesting because then we just go to the next step. Yes, so this is actually the odds, and I hope now it's clear. If there's this unbalanced energy situation where you have like over proportional energy on the one, let's say on the left side, and this energy is then also missing on the right side, then the probability that you get a left to right transfer is of course higher, because left to right transfer exactly happens if you randomly pick an up card on the left side, right? So the more richer a side is in energy, the more likely it is also to give it off. So there's like this pressure to hand it over until maybe stochastically the right hand side got a higher fraction of energy, and then the pressure is also in the other direction. So the these odds in this dynamical system where we have this rule that at the time step we should swap around energy is exactly going against one. I mean, I hope this is you're sold on this. The long-term development of these situations, and we can look at the graphs again. The long-term development is that the excess energy, if you want to call it, if the fraction is too high, it falls off, and then eventually it reaches the point around where the odds are around one, in both directions. And then, of course, stochastically things go happen, but if it goes too much out of bound, then there's an entropic pressure back again, and so it will forever then stay wiggling around the odds of 1. The odds are given as a function of exactly these ratios. It doesn't really matter in which polynomial form or 1 over the ratios, whatever. Because of this sort of symmetry, the odds go to 1, and so the odds exactly have, like the ratios have to become the same value for these odds to be 1. Okay, and then again, I plug this into ChatGPT. Compute please the total number of microstates for this energy split left and right, and divided by this energy split. So these are two. This is the fraction of 2 number of microstates where the energy situation is just 2 apart, right? So here is after a transfer left to right, here is before the transfer left to right. And these come out as odds divided by some expression, which if you plug in the numbers, if there's sufficiently big system, this the denominator is basically 1. You can ignore it. This is basically the odds. So the ratio of the microstates per fixed energy that are 1 apart is also basically the odds. So the system converging towards the odds of 1 corresponds also with the ratio of microstates converging to 1, i.e. where there is basically no change in microstates between like an individual jump, right? This is the 1 left to right jump, i.e. this is also the place where the number of microstates is extremal, so where it's like very flat. Right, this is something like you can read. This is of course a discrete system. This is not like you do not take a derivative in a calculus sense, but this represents basically the slope of the microstates function as a number of energy on the left side, and exactly where this is particularly flat, where there's like an extremal situation where the first derivative is 0, is the equilibrium situation. And this is the spoiler, in the thermodynamic theory there is no time or there's no probability. However, there is the entropy, which is basically the number of microstates, or rather it's a logarithm of the microstates to get something additive. And the equilibrium is we will see this in the next video, but it's characterized by the behavior of the entropy function, the microstate function, the statistical interpretation of entropy, of physical entropy. So the abstract thermodynamical system theory is really abstract, because you eventually speak about of derived macroscopic concepts, but you still have enough formalism to describe how different temperatures and different energies for particular state equations have to look like. Okay, this is just a motivation for the next video. Okay, and here I already basically said this. Equilibration is where this is 1, i.e. where these fractions are both on the same side. It does not matter which function of these fractions you have left and right to say that this must be the same. If f is monotone, then you can also express it like this. And spoiler, in this case, for the situation here, 1 over temperature up to a constant, like this is basically the coldness, is also called the beta parameter. 1 over the temperature is exactly such an f, where the f will be a logarithm. And if in this situation I can argue in combinatorics terms that the fractions on both sides must become the same. In the thermodynamic theory, it's then always just the temperature. Okay, and yeah, here spoiler ahead a little bit. So the entropy, I already said that, basically is the microstates, or rather the logarithm of the microstates, to not have multiplication but addition. Why it's that is the subject of the next video. And you work with the energy quantity U, which I also like implicitly have made use of in talking. You have these abstract entropy, and then you can just define more quantities, and the temperature is exactly defined just as some simple derivative, and then you have this abstracted system which behaves pretty much like our card game example. And of course, it's a physical system, so you do not just have energy and entropy. You also have the volume. You think of a piston. You think of the industrial age. They talk about pistons and stuff. There's volume, which also can change the energy, or rather, you can use the energy to change the volume in which the gas is pressed. There's the particles, there's also the small n. And so there's these quantities, and there's also this sort of mystical quantity, entropy, which 40 years later, when the atomic theory was established, can then be interpreted, be understood in terms of these microstates. This is the contribution of Boltzmann and Gibbs. I will not dive even too deep into this. You have, like, if you have volume, then you also have pressure. These are just the names given to the derivatives. You have the chemical potential from the particles. You have the temperature from the entropy. I will talk in the next video about the free energy, which is a good starting point if you already believe in temperature, and then you get the entropy as to sort of transform. The theory of phenomenological thermodynamics is sort of simple because there's not many moving parts, but on the other hand, it's also complicated. Like, you would think, oh, you're just taking derivatives and doing relations, but to the dismay of a few students, but it also makes it intriguing, I would say, it's not just like simple 101 differential geometry. You do not just have like derivatives of potentials, but you also have more complicated delta quantities which do not correspond to potentials, right? So if you have a gravitational potential and you say, I have some potential energy here, the stone falls down, it has a lower potential energy. If I pull it up again, it has the same potential energy as before it fell down. In thermodynamics theory, we play with about other differentials which are sort of path dependent. You know this by the entropy. It goes always up, right? You cannot go in a circle, or in general, it's more like complicated when you talk about these heat differentials, these delta Qs. And so there is like contact geometry, which is sort of the differential calculus of a lot of these things. But I'm just arguing here this is not as easy, sadly, as one would hope to be to describe all these thermodynamic systems. So, okay, yes, I think I'm pretty much through my content. I give you one last glimpse at my my images here. In the next video might be shorter. It's just pure thermodynamics theory. I will reference this video, and then we talk in the third video about the Q logarithm and some Lagrange optimizations and constraints that argue against Thales entropy and these kind of things. Okay, and with that, I wish you a good night.